All right, perfect. We'll move on to our next speaker, and that's Pavel Krasnopolski. And the title of his presentation is Beware the Red Light. Go ahead, Pavel.
Thank you. So my name is Pavel Krasnopolski. I am connecting from North York here in Toronto. And that's actually my second presentation for the Recreational Astronomy Nights. And some time ago, I asked myself a question of, well, we all know that it's recommended to use red light when going stargazing or doing amateur astronomy. So exactly how red should it be? And what kind of intensity it should be. And so I decided to take this kind of a deep dive into the workings of human eye and um, any kind of theory and numbers that I could probably come up with to quantify how appropriate different lights are. And so first I'll show some small demonstration here. So suppose you actually want to go stargazing. You heard that you need to use a red light at a dark sky site. So you probably look around your home and maybe you'll find something like, maybe like this bicycle light, right? Which is kind of red. I think you can see that it's red. And it's a red light. So is it good enough? Well, let's see. I will just dim the lights for a moment here, and I'll have a white surface to project the lights on. And so let's just project it here. So it's kind of red, yes. But here I have another source of light, and I'll talk about it later. And you can see that those are very different shades of red. And in contrast, the bicycle light looks almost yellow. So how bad is it? Is it no good, or maybe it's just good enough, considering you already have this light, I assume. Well, let's find out. So let's go back to the slides, and right there on the title slide, you see that was the picture that I took a month ago of the Carr Astronomical Observatory that belongs to Royal Astronomical Society of Canada. And you can see the whole facility uses dim red lights throughout. You can even see the telescope sticking up, looking into the sky there. So let's get to it and let's see why astronomers use this red light. In today's talk, first we'll need to discuss how the human eye works, how it adapts to darkness, why we need the red light, what are different sources, what are our options, and how those different sources of red light compare to each other. We'll try to compare and contrast them and maybe rank, find some hard numbers to rank them. And some options for actually getting one, maybe making one even. So let's start. You might have remember from your high school science lessons that human eye contains two types of receptors, cells that are sensitive to light, rods and cones. Rods are larger, which makes them more sensitive to very low light, so they capture much more light per each cell. On the other hand, cones are much smaller, but they give you better resolution. Chances are right now you're watching this presentation with your cones in your eyes. You will, of course, need rods to during stargazing because it involves very low levels of light. But occasionally you might also want to use your cones to read text or sky charts. And yes, on a couple of occasions I dropped parts from that very telescope that's behind me in the tall grass under dark skies, and I needed to find them. So that's why you kind of want to have both possibilities there. Here, you can also see the spectra, the sensitivity of the three types of cones and rods. Right, there's only one type of rods; they're not sensitive to color. And you can see that rods are sensitive to a narrower spectrum of light. So how exactly does the eye adapt to darkness? How exactly does it switch between the low sensitivity cones and high sensitivity rods? So that's what happens when the level of luminance or illumination changes. We're dealing with a huge dynamic range, right? So between starry night, you can see it's 10 to the minus 3 candelas per square meter, just a unit of amount of light. So this is 10 to the minus 3. You can go to the sunny day, which is about 3 times 10 to the 4, 30,000. So that's already a dynamic range of 30 million there. Actually, 300 million. But the eye can also withstand even higher amounts of light. You can briefly look at the sun without permanently injuring yourself. And you can also see in a very dark room without a starry sky around you at even lower illuminations. So we are definitely covering dynamic ranges of a billion and more. The very first mechanism by which the eye can adapt to darkness is by dilating the pupils, right? So this line here and this chart here shows you that the area of the pupil can increase 10 times. But this controls the amount of light to all of your retina, to all of your sensitive cells. So it doesn't really differentiate. And when in a very low light, this is called scotopic vision. And you only have your rods working really, and your cones work at very high amounts of light. That's called photopic vision. So exactly what happens when the level of light changes? You can see it on this graph. On the horizontal axis, you still have the amount of light, luminance in candelas per square meter, logarithmic axis. And on the vertical axis, you see the sensitivity. Now that's interesting because when you go into high levels of light, you can see the sensitivity dropping almost inversely proportional to your luminance, which means basically your eye wants to give the output in the same range. The signal that it sends to your brain should go, let's say, from 0 to 100% all of the time. And so if the amount of light is a lot more, then it has to turn down the sensitivity just to keep it within the range. And the thing is that cones start saturating and tuning down their sensitivity at much higher light levels. Roughly, this boundary is the upper boundary of the so-called mesopic vision, when you have the mixture of the photopic and scotopic visions. And of course, the rods start saturating at much, much lower light levels. In fact, the starry night here, which is something that you will experience during stargazing, the rods will already start to saturate a little bit, by maybe a few percent. So they can actually detect even lower light levels. And notice that the sensitivity is 2 orders of magnitude difference here. Of course, rods are much more sensitive. And from my experience, I actually measured it. To be able to read the text, I need about 0.3 lux of illumination. On a white page, it would give you about 0.1 candelas per square meter of luminance. So we're talking right about the middle of mesopic vision is what you need to just start to be able to read small text or see fine details. So that's where your cones roughly kick in and they start working. However, we have a paradox here because, of course, for stargazing, you need more than 100 times lower light level. Sorry. So here's what I want to read. Here's what I want my cone response to be. And here's what I need to stargaze. So here's what I need my rod response to be. Right? And of course, if I just shine a white light at 0.1 candelas per square meter, then I will saturate my rods by, well, about 30 times here. So which will be absolutely disastrous for my night vision and for ability to enjoy dim objects in the sky. So how can we have both of the worlds here? We need essentially a range of 100 times a difference between the rod response and the cone response. Well, the key to this is noticing that in the red light, so 650 or so nanometers, cones have significantly more response than rods. Even as you see the rods and cones curves adjusting to the light levels, still the red light is mostly the area where the cones really outperform rods. And even in the very, very low light, even under the essentially dark sky, the sensitivity of rods and cones is essentially the same, despite the overall sensitivity being 100 times difference. Which tells us that we should use red light. This is the primary reason. That's essentially the way to cheat around the different sensitivities. And if there's one thing that I wanted to remember from this presentation, it's this chart here. So what I did was I took the curves of sensitivity of scotopic and photopic visions, mostly rods and cones, from the website of International Commission of Illumination. They have reference spectra for a lot of things. I scaled it to 100. Again, because we saw in the previous graph that the relative sensitivities can change a lot with changing light levels. So the absolute values here don't matter very much. We can basically just normalize the peaks to 100. And then I plotted the ratio between them. The idea is that we want a certain amount of cone response. So we want to find this kind of the type of red light which produces the minimum rod response, the minimum possible one. So you would have the ratio of the rods to cones responses at the minimum. And you see this black line here, which is supposed to tell you that. Now, there are several lessons to learn from this. So first of all, the light at 680 nanometers wavelength is pretty much as good as it gets. There's almost no sense in going longer wavelength. You will only lose overall efficiency because, of course, the sensitivities keep dropping with longer wavelengths. So there's no point of going longer wavelengths. And if you go into shorter wavelengths, 660 nanometers is still mostly okay. It's a change of about 25% here. But then it starts deteriorating rapidly. So the rods will start picking up more and more light here from your flashlight. So these are the vertical lines here are different types of LEDs. And I'll show the comparison between them later. And there's also another way of creating red light, of course, is by using a filter. Here I'm using a particular type of filter, again, which I'll show in a moment. And the spectrum of it is shown here in dotted lines. Please note that this is a logarithmic scale. So the maximum here is at 80% transmission of the filter. Now half of that would be 40%, and that happens at 660 nanometers, which is roughly the cutoff wavelength for practical purposes. It has just a tiny tail of transmissivity here at about 2%. It doesn't affect the situation too much, and so we'll see in a moment. And just a little note about the LEDs here. So there are different wavelengths of typical LEDs that you can buy. Here's their again a collection of spectra of different LEDs. This one is the most common. It has the peak at about 630 nanometers, which is also the bicycle light that I showed earlier. But there are also others. Those are the ones that we probably want. Please pay attention to this shape of those spectra. There's quite a lot of light at shorter wavelengths, and of course the sensitivity of the eye increases with shorter wavelengths, which is why, despite having a peak at 630 nanometers here, the LED actually will have an effective or so-called dominant wavelength at about 620 nanometers. And for example, these ones, if you have a wavelength of 680 nanometers, the dominant one will probably be around 660. So now let's compare all of the ways that we can produce red light. So what I did here was essentially took a table of the spectra of sensitivity of the eye, and also spectra for some other things like incandescent light bulbs, like white LEDs, also multiplied by the transmission of that filter that we showed in the graph, and just bare white LEDs. And so those numbers, those are those ratios of rods to cone sensitivity. You don't need to pay attention to the absolute value of this number, because again, it's somewhat arbitrary. Both sensitivities were scaled to be 100 at the peak. But what you should pay attention to is how those numbers compare between different sources and different wavelengths. Right? So the red LED, which is marked as peak wavelength 680 nanometers and dominant wavelength of 660 nanometers, is almost ideal. It's just about 25% worse. There's also the types of LEDs that are sold for example, grow lights, for also deep red lights, for example, photographic processing, photo red. They're called different things, but they're all have a peak at 660 nanometers. Those are somewhat worse, but still generally tolerable, right? And then you can go to other options. You can have incandescent lamps with a filter. You can have the common red LEDs, again, right, like in the bicycle light that I showed you. You can have white LEDs with the filters, and those progressively get worse. Already the cool white LED with the temperature of 5000 K will be about 7 times worse than the ideal, and more than 5 times worse than the 680 nanometer LED. And of course, just pure white sources are absolutely terrible. Please do not use bright white lights at, for example, dark sky preserve or any stargazing location, because you can see those numbers are more than 100 times worse than ideal. So you have this. Actually, another way of putting this: if the white light produces about the ratio about 1/2, and your red LED produces about 0.005, that means that we have that 100 times improvement over the white light of the sensitivity of rods and cones, right? The ones that we said we need to simultaneously use actually both rods and cones, be able to read a sky chart and be able to stargaze. So let's look at those sources. So first of all, I'll show you the filter. So this is a particular type of filter. It's used in stage lighting. It's usually sold in those sheets, 24 by 20 inches. There are several companies making them, and there's a huge selection of different colors and different types. But this one, number 787, called Marius Red, is the only one that I found that has this good spectrum with a cutoff longer than 650 nanometers. And it looks very, very dark. Here I have even a thinner strip of it. You can see that you can still see the my lamp through it that I have in my room, but it's quite dark. Despite having transmission of 80% in the deep red, it cuts off everything else, which is why it's dark. These are usually available quite cheaply for about $10 for that piece, depending on your source. Now, there's also, well, I've already shown the red 635 nanometers or so light, like this. Your other option would be to take a white light, like this one or like this one, and then cover it with a layer of that red film. Right? You can see how much the red film decreases the overall brightness because it cuts off all the wavelengths there that you don't want. And of course, you can go for just pure 680 nanometer LED, and that's the source of light that I showed in the very beginning, right? That's here. I just have a simple module here attached to some wires connected to power with a bit of lens there. That could be an option for if you're more inclined towards DIY options. Those LEDs can be sold, or they can always be sold as just usual 5 or 3 millimeter LEDs like this. But take note that these are not very powerful. Sometimes you might need currents that these LEDs are not capable of, and you can buy more powerful LEDs, sort of something like this. It's a heatsink mounted module, and then work with that. And then, of course, there's a huge selection of different lenses. Usually, they can be found very cheaply for large packs like this. So let's see how this chart works in practice, right? So I'll just bring back my stand here, and we'll set out the light sources from the worst, like this white, cool white LED flashlight, from the worst through the kind of okayish to good and to the best. Right, so once again, this is, you have the white LED, absolutely terrible for stargazing. This is red bike light, just any kind of red light that you would find around your house. This is the filtered white, using that gel filter for stage lighting. And this is pure 680 nanometer LED here. So let's take the sheet of this filter, and let's see what it does to these lights, and pay attention to the intensity, right? So immediately you see that it cuts a lot of light from the bike light, and it cuts a lot of light from the white flashlight. But if you look towards the better options here, the change of light is actually quite minimal there. So we can tell that the filtered white and pure 680 nanometers LED are actually pretty good. There's almost no reduction in their brightness, which means they already have just the good wavelengths that we want to work with. On the other hand, the bike light, despite technically being red, you can see a lot of that light gets cut off, to the extent that the brightness of the bike light is almost the same as the brightness of the white LED through the filter. And the reason for that is that this LED, this sort of red LED, doesn't actually have the wavelengths that we're interested in. If you go back to the to our spectra there, right? This is the bike light here. We want spectra that's we want wavelengths that are longer than 650 nanometers, but it doesn't have any, almost none. Which is why when you filter it, you cut off so much light. And so there's basically no advantage of starting with a red light if you are going to filter it. Now, of course, if you don't want to filter it, then having at least some kind of red light is still better than nothing. So let's summarize, right? What are our options? Cheap and quick is the red filter, and you saw that yes, indeed, we can use it and obtain pretty good spectrum. They are called gel filters. They used to be made on gelatin, but now, of course, it's just cellulose acetate. About $10 per pretty large sheet. This is the only type that I found which is suitable, 787 Marius Red. You can use it on white LEDs. You can use it on incandescent lamps. You can use it on your phone screens. It's pretty good for that. Using it on red LEDs is, well, frankly, doesn't make much sense, in my opinion. And it does cut off a lot of light. So paradoxically, you might need stronger white source, despite wanting to achieve a dim red source. But because so much light is getting cut, you might need to start with a brighter white source. And unfortunately, it's usually difficult to contain the stray light. You will need to use a lot of dark tape around your light, because even small leakages of white light will probably ruin your picture, because that white light is much stronger than the red that goes through. Now, not as cheap, but still cheap. Common red lights, like the bicycle light that I showed. It's better than nothing, but the wavelength is too short. So we saw it's at least twice worse than the ideal. Slightly better than filtered white. And another thing I found is that it's just way too bright by itself. That bicycle light had to be dimmed about 3 times before I was kind of satisfied with the intensity of it. And I did test it in a dark sky area. You could use the filter, but only to make it dimmer, essentially. Now, the best ones would be, second best ones would be the 660 nanometer LEDs. They're used for grow lights, etc. It could be good enough for most purposes. The advantage over the longer 680 nanometers is that usually it's easier to find, usually easier to source. And of course, at those wavelengths, you don't need a filter. And the absolute best, of course, is the 680 nanometer LED. It's almost ideal. Usually, you would need to buy them in, modest bulk, maybe 10, 20 at a time. yeah, so for the if you want to experiment with it yourself and you want to actually source them, here's some of my recommendations. I actually tried all of this experimentally. Sorry about this. The I found the best lens is the 30 millimeter, 30 degree angle lens. This is the lens that I have on the actual LED that I just showed. When you have the lens with the reflector, it usually outputs more of the light and doesn't produce as much of a stray light. With these LEDs, I found that the current of about 30 or 50 milliamps is good for walking and seeing several meters ahead of you, including seeing the grass and being able not to break your ankles. And you can use the dimmer lights if you just want to read sky charts. So for just for reading, you would you could use a single small LED, which they usually go up to about 20 milliamps. And for slightly brighter purposes, you might need a bigger LED or maybe a couple of smaller ones. So this basically is all that I have today. I'll take some questions.
Great. Thank you so much for your presentation, Pavel. It was great to learn about the theory and then to see the actual demonstration. So well done with your presentation. Thank you again. Anya, do we have any questions for Pavel?
Yeah, we have a question from Betty who asks, what manufacturer and what supplier can you recommend for the 787 Boreas light?
So usually those sheets are made by two major companies. There is Lee Filters and there is Roscoe. They both cost about the same, and the spectra are nearly identical, so it's more or less standardized. So again, Lee Filters and Roscoe is what I kept finding. The one that I have here is from Lee Filters. There are several stores around Toronto. I'm not sure if it's to be appropriate to say those right now, but yeah, there are some stores. I mean, usually the search the keywords that you want to type into let's say Google, it's just the 787 Marius Red, and yeah. Again, do you want me to give examples of where to buy them?
Sure, I think that'll be fine.
Okay, well, there's one place in Etobicoke. It's called Source Shop, the Source Shop, with the same website, sourceshop.com. And you can buy anything from the 24 by 20 inch sheets there to 25 feet rolls. Of course, bulk orders are cheaper. That's just the ones that I bought those from a few years ago, and yeah, it's usually within about $10 per this sheet.
Okay.
And we have a comment from John Wunderlich who says, nice and effective demonstration, thanks. Followed by Betty with, so true. It would disentangles the question of which lights are best and why.
So which lights are best and why? Essentially, this table is supposed to summarize it, right? I would say if you want to just put something together quickly, is you would use a filtered red. So you would use that filter, and you would tape it onto a white flashlight like this. But again, make sure you check it, because the white flashlight should be sufficiently bright initially, because when you tape it over with the filter, it becomes quite dim. So this is easy to make and very quick. You do need to buy the filter. Otherwise, well, if you look on web stores, Amazon and like, there's a lot of flashlights that are called for astronomy, for stargazing, and dark, etc. If they don't specify the wavelength that they have, assume that it's just the cheapest 630, 640 nanometers, like this one. So it will not be as good, but it'll be better than nothing. So do go with just red flashlight if you don't have anything else. Try to find something that specifies a longer wavelength in the description of the product, or use a filter.
And our last question is from Ronan of Stag. Sorry if you went over this already and I couldn't parse what you were saying, but what is the difference between the initial red light you shared and red shifted, please?
So the initial, I guess it's what was the initial comparison that I did in the beginning. So again, this is the most common one that has the a wavelength of 630, 640 nanometers, and this one is 680 nanometers, right? So with when you have a dedicated long wavelength LED, you don't need to filter it. You can basically just use this as your flashlight. With this one, you might try to filter it, but it will still be a bit inferior. And again, if you go back to the chart in the presentation, you see that this most common LED is about 3 times worse than the 680 nanometer LED. So for the same amount of the response of your cones, if you adjust the brightnesses of all your flashlights to produce the same ability to read text or work with small parts, then the common LED will have 3 times as much effect on your rods. I guess that's the main lesson to learn from this.
Okay, thank you.
Okay. And one of our AV technicians, Ward LeGros, mentioned to me that he also has access to these gel filters, and he would be able to supply them through our membership for a cost, I imagine. So again, Ward LeGros, you can probably catch up with him at our next meeting, which will probably happen in person. So Pavel, thank you so much for the demonstration and the presentation.